Hi, in this video I'm going to present you a script that automatically creates in DIgSILENT the admittance matrix of any complex power system. So we all know that DIgSILENT doesn't allow us to access the admittance matrix, so therefore this script is going to create it for us. Actually, this video is a continuation to an older video of mine, but that video was that script was for a very simple power system. This is for almost any type of power system. We are going to see further. Okay, so the main idea is when creating the admittance matrix is to compute the admittance diagonal elements. So for any diagonal element, we have the sum of all series admittances plus the sum of all half shunt admittances. And for the non-diagonal elements, we have minus sum of all common series admittances between those two buses. Okay, so let's see in what case the script is not going to work. So the script is not going to work for a 3-winding transformer if the tap changer is on the low voltage side, if there are more than one tap changer, if the phase of the voltage for tap is taken into consideration, and if the shunt elements are of type LLC, ERP, so on and so forth. So I didn't consider this points because they are very rare, so that's why. Okay, so let's see the system. So we have here a simple power system with 4 nodes. 1, 2, and 3 are 110 kV, and node 4 is 220 kV, in which we have 2 transformers and 3 lines. Okay, how we are going to compute the admittance, admittance matrix for this power system? Just executing the script. Okay, we have here the admittance matrix in complex form, so every element is a complex number. By the way, DIgSILENT doesn't work with complex numbers, so that's why I was forced to create another subscript in which creates which make operation with complex numbers. Okay, so based on this admittance matrix, we are going to compute the currents, which is the product between matricial product between the admittance matrix and the complex voltages, bus voltages taken from DIgSILENT. With those injections, we are going to compute the apparent power injections in each bus, which is the product between bus voltages in complex form multiplied with the conjugate of the current vector that we previously computed. And further, here we have the measured apparent power injections. These values are taken from DIgSILENT and compare with our computed apparent power. If R equal, yeah, we should obtain here in the error 0 for active power and reactive power for each node. This is a way to validate our script. Yeah? Attention that this holds only if in the network are not considered the shunt admittances. Yeah, if the susceptance conductance of the lines and for the transformer and for the transformer are taking into consideration no load current and no load losses, then this doesn't hold. Yeah. So if the shunt admittances are not taken into consideration, are not introduced for the lines and for the transformer, we should obtain 0 in the error 0 in each bus. Yeah. Okay, so let's verify our admittance matrix. So we are going to export this power system to another software in Power World simulator. So I'm going to export it as a PSSE file, and I'm going to import it in this software where we have access to the admittance matrix. Yeah. Okay. Here we have the YBus. Now let's compare it. Yeah. Let's see. So as we can see, comparing each element from the both software, we can see that they are the same. Yeah. So now let's do something else. Let's complicate things a bit. So we are going to consider, here we have some shunt elements. Here we have an RL element with maximum of steps 3. We're going to put here 2, 10 megavar, and here a C shunt with maximum number of steps 2. I'm going to put here 1 with 7. Yeah. Let's consider some magnetizing susceptance for the transformer. Let's put here 10%, and let's put for the other transformer 15%. Let's see if it holds. So now we are going to try to complicate things a little bit. For this line, we are going to put here a susceptance of 3000. We are going to put 2 parallel lines with 4 kilometers. So we are in this way we are going to complicate with 2 transformer here. Let's see if it holds. I hope it holds. Yeah. And let's put here, yeah, 2000 with 2 lines. Yeah. Okay. And something else, we are going to consider the plot of the transformers, position 1 for this transformer, and for this transformer I'm going to put -2. Let's see if it holds. Yeah. And also, last thing, I'm going to put a phase shift of 150 degree actually. Here also in this 5. And now we are going to compute it holds. Now we are going to compute the admittance matrix for this complicated scenario. Yes. So let's execute the script. Because we introduced the shunt admittances for the lines and for the transformer, you can see the error doesn't hold anymore. This is the admittance matrix, and we are going to export the admittance, the power system in the Power World simulator. Okay. Now we are going to determine here also the admittance matrix and compare the 2 admittances to the 2 matrices. Okay, let's see if it holds. 30, 18, 94, 18, 85, 50, 34, 94, 50, 11. Yeah, so we can see that the admittance matrices are identical for this complex scenario. So yeah, that's it. We can see that we obtain good results for a multitude of types of element and variable taken into consideration. We are going to take into considerations how many transformers in parallel do we have, how many lines in parallel do we have, the length of the lines, the phase shift, yeah, the plot of the transformers, and the shunt admittances for the transformer and the line. Yeah. So we see that we obtain the same admittance matrices. Yeah, that's it. Thank you so much.